A warp drive is a theoretical engine that wouldn't propel a ship through space, but would instead bend space itself. By contracting space-time in front of a spacecraft and expanding it behind, the ship could appear to move faster than light without actually breaking that limit. Inside this warp bubble, the craft would remain still while space does the moving. It's a brilliant concept that blends science fiction with serious physics, a loophole that could, in theory, make interstellar travel possible. But if the idea works on paper, why haven't we built one yet? Watch this video till the end to find out, and subscribe to the channel. Let's begin. If bending space could let us outrun light itself, then why does humanity still crawl through the cosmos at a snail's pace? The math behind warp drives, elegant, daring, and grounded in Einstein's own equations, suggests they might be possible. Physicists have written the formulas, sketched the bubbles, and calculated the curvature of spacetime itself. Nothing in the math explicitly forbids the idea. And yet, we have no warp ships, no glowing engines, no folded corridors of spacetime whisking us to Alpha Centauri. This paradox, between what seems theoretically allowed and what's practically achievable, is what makes the warp drive such a fascinating mystery. It forces us to confront a deeper truth about science. Possibility on paper doesn't guarantee reality in practice. Our equations might describe the dance of warped space, but nature may have built walls around certain dreams that we don't yet know how to climb. Perhaps the universe has a way of teasing us, showing us glimpses of extraordinary potential just out of reach. Or maybe, the barriers we face aren't in the math at all, but in our understanding, our technology, and our sheer energy limitations. To find out, we need to start at the foundation, with the physics that built the very rulebook of reality itself. Einstein's theory of relativity is both the foundation of modern physics and the ultimate roadblock to faster-than-light travel. According to his special theory of relativity, the speed of light, about 300,000 kilometers per second, isn't just a really fast number. It's the cosmic speed limit written into the very fabric of spacetime. Nothing with mass can reach or exceed it, because as an object moves faster, its mass effectively increases, demanding exponentially more energy to keep accelerating. By the time you approach light speed, the energy required becomes infinite, and since infinite energy doesn't exist, the journey ends there. This isn't a suggestion or a technical obstacle. It's a fundamental feature of how the universe operates. The closer you get to light speed, the more warped your perception of time and space becomes. Time slows down for you, distances contract in your direction of travel, and energy costs skyrocket. For a spacecraft trying to break that limit, the rules of physics themselves seem to push back harder and harder until movement becomes impossible. Light, having no mass, can travel at this ultimate speed. But for everything else, from the smallest particle to the largest ship, that barrier is absolute. So, Einstein's relativity doesn't merely slow us down, it defines the structure of motion and time itself. Yet, ironically, it's also his broader theory, general relativity, that opens the door to the warp drive idea. If we can't move faster through space, maybe we can manipulate the shape of space around us. And that's where a radical new idea enters the scene, one that dares to twist Einstein's own equations into something extraordinary. In 1994, a young Mexican physicist named Miguel Alcubierre published a paper that would change the landscape of theoretical physics and reignite humanity's most ambitious dream: faster-than-light travel. Building upon Einstein's general theory of relativity, Alcubierre proposed a model that didn't break the laws of physics, but instead bent them in an astonishingly clever way. His idea was simple in concept, yet mind-bending in implication. If nothing can move through space faster than light, then why not move space itself? Alcubierre's solution, now famously known as the Alcubierre drive, describes a theoretical warp bubble surrounding a spacecraft. Within that bubble, space-time in front of the ship would contract, essentially drawing the destination closer, while space-time behind it would expand, pushing the starting point farther away. The ship itself wouldn't technically move at all. It would sit at the center of this bubble, motionless relative to the warped space inside it. Yet, to an outside observer, the entire bubble could appear to move faster than light, carrying the ship along with it. What made Alcubierre's idea revolutionary was that it didn't violate Einstein's relativity. Locally, meaning inside the bubble, the ship never exceeded light speed. The laws of physics inside that region remained intact. However, the geometry of space-time around the bubble was distorted in such a way that the bubble itself could effectively cross interstellar distances in a fraction of the normal time. In theory, a ship powered by this drive could travel from Earth to the nearest star, Proxima Centauri, in just days or weeks rather than tens of thousands of years. Alcubierre's paper wasn't just a flight of fancy. It was grounded in the mathematics of general relativity. His equations showed that space-time could indeed be manipulated in this way, at least theoretically. The trick lay in shaping the curvature of space-time through an energy distribution that created the warp bubble. Space ahead would be compressed, space behind would stretch, and the ship would ride the resulting wave like a surfer on a cosmic tide. In many ways, this concept mirrors what we already know about the universe. Space itself can expand faster than light. During the Big Bang, cosmic inflation caused regions of the universe to expand at superluminal speeds, not by moving through space, but by stretching space itself. Alcubierre's model borrowed that same logic, using space-time's flexibility as a means of propulsion. However, while the math was elegant, the implications were staggering. To produce the required curvature of space-time, Alcubierre's equations demanded a type of energy that had never been observed, negative energy density, or what's often called exotic matter. Unlike ordinary matter, which has positive mass and energy, exotic matter would generate a repulsive gravitational effect, allowing space to warp in the necessary way. In essence, to create a warp bubble, you'd need something capable of pushing space apart instead of pulling it together, something opposite to normal gravity. The reaction from the scientific community was a mixture of excitement and skepticism. On one hand, Alcubierre's drive offered a tantalizing loophole in physics. A mathematical framework that didn't break relativity yet allowed faster-than-light travel. On the other hand, it introduced requirements so extreme that they bordered on the impossible. The concept was an intellectual marvel, but also a reminder of how far our understanding and our technology lagged behind our imagination. What Alcubierre accomplished wasn't the invention of a practical engine, but the opening of a doorway in physics. He showed that, at least in principle, relativity didn't absolutely forbid interstellar travel within a human lifetime. It simply required us to think differently, to stop seeing space as a passive backdrop and start viewing it as something dynamic, shapeable, and perhaps even navigable. Yet as soon as the euphoria of this breakthrough settled, reality reasserted itself. The equations that allowed a warp bubble to form also demanded staggering amounts of energy, quantities that seemed to dwarf anything humanity could ever hope to harness. For all its elegance, the Alcubierre drive came with an astronomical price tag. And so the next great question emerged. Even if the math works, could we ever hope to power such a device? At first glance, the idea of traveling faster than light sounds like pure heresy against Einstein's laws. Yet the genius of the Alcubierre drive lies in how it avoids breaking them entirely. The trick is not to move the ship faster than light, but to manipulate the very stage upon which all motion occurs, spacetime itself. In Einstein's framework, space and time aren't separate rigid entities. They're part of a flexible, dynamic fabric that can stretch, compress, or curve in response to energy and mass. What Alcubierre realized was that by reshaping this fabric in just the right way, you could make a ship appear to move faster than light from the outside, while locally, it never actually violates relativity at all. Inside the warp bubble, the ship is in a region of perfectly flat spacetime. No acceleration, no time dilation, no relativistic strain. To the people on board, the universe outside is simply flowing past. The bubble itself does the heavy lifting by contracting space ahead of it and expanding it behind. From the ship's perspective, it's just sitting still in a calm pocket of space, while the universe literally rearranges itself around it. To an outside observer, however, that pocket could traverse enormous distances faster than light could ever travel through unwarped space. This is where the concept becomes truly mind-bending. Einstein's relativity forbids motion through space-time faster than light, but it doesn't forbid space-time itself from expanding or contracting at any rate. We know this from cosmology. During the early moments of the Big Bang, the universe underwent a period of inflation, expanding far faster than the speed of light, not by anything moving faster, but because the metric of space itself stretched. In other words, space-time can outrun light, and Alcubierre's warp bubble exploits that loophole directly. So, relativity isn't being broken, it's being bent. Locally, within the bubble, the ship never exceeds light speed relative to its immediate surroundings. This keeps all the laws of physics intact within that region. But the shape of space-time beyond the bubble changes, and the curvature effectively carries the ship across cosmic distances at apparent superluminal speeds. Think of it like riding on a moving walkway at the airport. You're walking at your normal pace relative to the floor beneath you, but to an observer standing still, you appear to move much faster. Except in this case, the walkway is the universe itself, folding and stretching as you glide across it. This elegant loophole makes the warp drive concept uniquely compelling because it stays true to Einstein's equations. It doesn't require rewriting physics, only applying it in an unconventional way. The ship avoids the problems of infinite energy and relativistic mass increase that plague any attempt to accelerate near light speed. There's no time dilation to freeze your clocks or stretch your atoms. Inside the bubble, physics behaves as comfortably as it does on Earth. However, while the theory fits within general relativity, it introduces new challenges that push the limits of our understanding. For one, the creation of such a bubble would require control over space-time curvature on a level we can't even begin to achieve. Moreover, the mechanism for expanding and contracting space-time in such a controlled manner demands energy forms that don't exist in any usable form, specifically negative energy. It's as if the universe grants permission for the warp drive to exist on paper, but hides the key ingredient behind layers of cosmic secrecy. Still, this mathematical consistency is what makes the Alcubierre concept so tantalizing. It doesn't throw out Einstein's theories, it dances within them. It's a proof of possibility wrapped in impossibility, a theoretical door left slightly ajar, hinting that maybe, under the right conditions, space itself could become our vehicle. But as the next obstacle reveals, the universe doesn't give up such shortcuts easily. Because while relativity allows the loophole, the price to open it is energy, an almost unimaginable amount of it. When Alcubierre first ran the numbers on his theoretical warp drive, the results were staggering, and frankly, devastating to anyone hoping it could ever be built. His equations showed that to create the space-time distortion necessary for even a small warp bubble, the amount of energy required would be beyond comprehension. In fact, early estimates suggested it would take more energy than what exists in the entire observable universe. This wasn't just a little more than humanity could currently produce. It was so absurdly high that even the combined output of every star, planet, and galaxy wouldn't come close. To understand why, it helps to remember what the warp bubble actually does. It isn't just moving space, it's reshaping the geometry of space-time on a colossal scale, compressing and expanding vast regions in front of and behind the ship. That kind of curvature doesn't come cheap. In general relativity, space-time bends in response to energy and mass. To bend space enough to achieve faster-than-light apparent motion, the warp bubble must generate gravitational effects billions or trillions of times stronger than anything nature produces outside of black holes or neutron stars. And while a black hole's gravity comes from concentrated positive mass, the warp bubble requires something far stranger: negative energy density. In Alcubierre's original calculation, the mass energy needed to create a bubble just a few hundred meters across was equivalent to the energy output of all the stars in the universe combined. It wasn't just impractical, it was cosmically impossible. Even if humanity harnessed the total power of our sun, it would still be less than a billionth of what was required. And this wasn't even taking into account the energy needed to control, stabilize, or move the bubble. This was merely what it would take to create it in the first place. Later refinements and alternative formulations attempted to bring those numbers down. Some physicists, such as Chris van den Broek in 1999, proposed modifications to Alcubierre's original geometry that drastically reduced the energy requirements, at least on paper. His model suggested that by shrinking the inner space of the bubble and adjusting the curvature of its walls, the total energy could be reduced to something only comparable to the mass energy of a few massive planets, or perhaps even a large asteroid. That was still unimaginably huge, but it was a step towards something less absurd than the energy of the entire cosmos. However, even these optimistic versions face a fundamental problem. The energy they call for must be of a type we don't know how to produce or even confirm exists in usable quantities. Normal energy, from fusion, antimatter, or black holes, simply wouldn't work. The warp bubble's equations require regions of space-time with negative energy density, which would act as a kind of repulsive gravity, pushing space apart instead of pulling it together. This exotic form of energy is something our universe might allow in theory, but so far, we've only seen the faintest hints of it in extremely subtle quantum effects. So the energy problem isn't just about magnitude, it's about type. Even if we could somehow gather the total energy output of a star, it would still be the wrong kind. It's like needing to fill a balloon with negative air, a concept that makes sense in theory but has no practical equivalent. This leaves us facing a harsh truth. While relativity doesn't forbid warp travel, the energy requirements effectively do. The universe may tolerate faster-than-light motion mathematically, but it has set the entry fee far beyond our reach. Still, science is relentless in its curiosity. Where one generation sees impossibility, another sees a challenge. Researchers began to ask whether there might be a way to produce or harness the needed energy more efficiently, perhaps using quantum effects, vacuum fluctuations, or undiscovered physics that could act as a source of negative energy. This question naturally leads us to the next great hurdle in the story of the warp drive, the mysterious and elusive concept of exotic matter. The heart of the warp drive concept, and its greatest obstacle, lies in something both fascinating and frustrating: exotic matter. This is not the dark matter that astrophysicists chase across galaxies, nor the ordinary matter that makes up stars, planets, and people. Exotic matter is a hypothetical form of material that possesses negative energy density, a property so bizarre that it would repel rather than attract gravity. In Alcubierre's model, this negative energy is not optional. It's the linchpin that makes the entire warp bubble possible. Without it, the equations collapse and the bubble cannot form or remain stable. In normal physics, mass and energy curve spacetime in one direction, inward. Massive objects like stars and planets warp the fabric of space, creating the familiar well-shaped gravitational fields we all understand. Exotic matter would do the opposite. It would curve spacetime outward, creating a region where space is pushed away rather than pulled in. To construct a warp bubble, you'd need a shell of this negative energy surrounding your ship, expanding space behind it and contracting it ahead. This shell would act as both the engine and the shield, protecting the craft from the intense distortions at its edge while propelling it forward by manipulating space-time itself. The problem? We have never observed, created, or contained exotic matter in any meaningful quantity. The concept isn't pure fantasy. It does appear in certain theoretical contexts, particularly within quantum field theory. Some quantum effects can produce fleeting regions where negative energy exists for extremely short periods of time. The most famous example of this is the Casimir effect, in which two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force. This effect arises because the quantum vacuum between the plates has a lower energy density than the space outside them. In essence, a tiny pocket of negative energy. However, the Casimir effect is minuscule. The amount of negative energy generated is so small that it could barely lift a dust particle, let alone power a starship. It shows that negative energy can exist under the laws of quantum physics, but scaling that up to the levels required for a warp drive is like trying to power a city with the static electricity from a single balloon. Moreover, even if we could somehow amplify the effect, there's no known method to stabilize or control negative energy without it dissipating almost instantly. This is where theory collides with the hard wall of reality. In Alcubierre's equations, the warp bubble must have precise regions of negative and positive energy density, balanced delicately across its surface. Too much or too little in any area, and the bubble would collapse, potentially destroying everything inside. Even if we had the right type of energy, the engineering precision required to shape spacetime on that level is far beyond anything humanity can imagine today. What makes exotic matter so enticing, though, is that its existence wouldn't just make warp drives possible, it would revolutionize physics itself. It could enable stable wormholes, anti-gravity fields, and perhaps even control over dark energy, the mysterious force accelerating the expansion of the universe. In many ways, the search for exotic matter overlaps with the search for a deeper understanding of the quantum vacuum. The idea that empty space is not truly empty, but seethes with virtual particles and fluctuating fields. Some physicists speculate that if we ever learn to manipulate these fluctuations directly, we might be able to mine negative energy from the vacuum itself. But as of today, exotic matter remains a ghost, hinted at in equations, glimpsed in quantum effects, but never held or harnessed. Without it, the warp bubble remains a mathematical mirage, beautiful, consistent, and utterly untouchable. Yet the mere possibility that negative energy could exist gives scientists a reason to keep pushing. After all, a century ago, antimatter was purely theoretical too, and now we can produce it in laboratories, albeit in vanishingly small amounts. Perhaps exotic matter awaits a similar discovery, locked within the quantum mysteries we've only begun to explore. Still, even if we could somehow obtain this elusive negative energy, another problem would immediately arise, one that's equally formidable. Creating the bubble is one thing. Keeping it stable long enough to carry a ship safely through warped spacetime is another matter entirely. The next challenge lies not in the energy source itself, but in the fragile, unpredictable nature of the warp bubble once it forms. In our search for the strange and elusive substance known as exotic matter, one experimental phenomenon often enters the conversation: the Casimir effect. It's one of the few real-world observations that hint at the existence of negative energy, a cornerstone requirement for any theoretical warp drive. But while it's fascinating and real, it's also vanishingly small, the faintest whisper of the kind of cosmic-scale energy we'd need to even begin bending space-time. The Casimir effect was first predicted in 1948 by Dutch physicist Hendrik Casimir. He proposed that if you place two uncharged, parallel metal plates extremely close together, just a few nanometers apart, a strange force would push them toward each other. This happens because the vacuum between the plates isn't truly empty. Quantum mechanics tells us that even in a vacuum, energy constantly fluctuates. Virtual particles pop in and out of existence, creating what we call zero-point energy. However, between the plates, only certain wavelengths of these quantum fluctuations can exist, while outside, all wavelengths are allowed. This difference in energy density creates a pressure imbalance, effectively generating a small region of negative energy between the plates. It's a remarkable demonstration that the vacuum itself isn't a void, but a restless sea of invisible activity. In that tiny space between the plates, the energy density is lower than in the surrounding vacuum. In other words, it's negative relative to normal space. And that's exactly the kind of phenomenon the Alcubierre drive would need to exploit on a vastly larger scale. Regions where energy behaves oppositely to how it normally does, pushing space-time outward instead of pulling it inward. But here's the catch. The Casimir effect produces an amount of negative energy so absurdly small that it's almost comical compared to what a warp drive would require. The force is measurable only in laboratory conditions with precision instruments, and the total energy involved could barely move a speck of dust, let alone propel a spacecraft across the galaxy. To put it in perspective, even if you covered an entire planet in Casimir plates, the combined negative energy would still be negligible, nowhere near the levels needed to warp space-time on a human scale. Still, the importance of the Casimir effect lies not in its magnitude, but in its proof of principle. It shows that negative energy isn't a total fantasy. It can exist under the right conditions, consistent with known physics. That tiny spark of possibility has inspired generations of physicists to explore whether quantum fields and vacuum fluctuations could be engineered or amplified in ways we haven't yet discovered. Some theoretical approaches suggest that manipulating electromagnetic fields, quantum resonances, or the geometry of space-time at the microscopic level might one day allow for controlled regions of negative energy. However, even with this tantalizing evidence, we remain at the absolute infancy of understanding how to use it. The Casimir effect is like discovering a candle flame and realizing it's made of the same stuff as the stars. The scale and control required to transform that faint phenomenon into something cosmically powerful are almost inconceivable. It's a reminder that while quantum mechanics opens doors to phenomena beyond our intuitive understanding, it also humbles us with its scale. In essence, the Casimir effect whispers that negative energy is possible, but it also shouts that we're nowhere near being able to harness it. It's the faint echo of a future technology that might one day make warp drives a reality, but for now, it remains a fragile clue, not a solution. And even if we could somehow generate enough of it, the next problem would immediately confront us: stability. Creating a warp bubble is one thing. Keeping it from tearing itself apart or collapsing in an instant may prove an even greater challenge. Even if, by some near miraculous feat, humanity could find a way to generate the negative energy required to form a warp bubble, another enormous obstacle looms before us, one that might render the entire concept futile: stability. Theoretically, a warp bubble could exist, but keeping it stable long enough to actually use it for travel could be nearly impossible. Like a soap bubble floating in a hurricane, the delicate balance of energy that defines its shape could collapse from the slightest disturbance, ending in catastrophic results for anything trapped inside. To understand why, we need to look at how the warp bubble works in Alcubierre's model. The drive requires an extremely precise configuration of space-time curvature, an almost impossibly fine distribution of negative and positive energy densities. The slightest imbalance could cause the bubble to fluctuate, distort, or collapse entirely. Remember that this isn't a material structure held together by physical walls. It's a purely geometric phenomenon, a region of warped space-time defined entirely by gravitational gradients. That means any disruption, even a minute quantum fluctuation, a stray particle, or a small irregularity in the energy field, could send ripples through the bubble's fabric, destabilizing it in unpredictable ways. Worse yet, the mathematics of general relativity suggest that the region at the front edge of the warp bubble, the so-called horizon, behaves much like the event horizon of a black hole. Inside the bubble, light and information can travel normally, but they cannot cross the front boundary to influence the bubble's leading edge. This creates a paradoxical situation. The very region that controls the bubble's movement and stability is inaccessible to anyone inside it. The pilot of a warp ship wouldn't be able to steer, slow down, or even know what's happening at the front of the bubble. In essence, once the warp field forms, the ship becomes a passenger on a runaway pocket of distorted space, unable to interact with the universe ahead. This issue, sometimes called the horizon problem, has enormous implications for stability. If the bubble can't be controlled from within, then any external disturbance, a gravitational wave, a cosmic ray, or even the irregular density of interstellar space, could alter its structure, and there would be no way to compensate. One tiny imbalance in the negative energy field, one unaccounted for fluctuation, and the bubble could implode, crushing or vaporizing everything inside. Alternatively, it could disintegrate unevenly, exposing the interior to immense tidal forces that would tear it apart. Even theoretical simulations of warp fields have shown alarming signs of instability. As physicists modeled the equations, they found that warp bubbles could emit massive bursts of radiation during formation or collapse. In some scenarios, the energy distortions became so extreme that they essentially destroyed the bubble from within. This isn't just a matter of fine-tuning or engineering precision. It might be a fundamental consequence of how space-time responds to such intense manipulation. Some studies suggest that maintaining the precise space-time curvature needed for stable, faster-than-light motion could require continuous adjustments on scales smaller than the Planck length, the smallest meaningful unit in physics. In other words, the stability demands precision beyond what the universe itself seems to allow. Another layer of complexity comes from the quantum realm. Quantum field theory tells us that space-time isn't smooth and continuous at very small scales. It's jittery, chaotic, and filled with random fluctuations. These quantum foam effects could easily interfere with the warp bubble's boundaries, triggering spontaneous collapse. Even if the bubble could somehow resist such disturbances, the energy needed to maintain its balance would be enormous and constant, effectively requiring the drive to fight the natural instability of the universe at every moment. Some physicists have tried to propose ways around this. A few suggest that it might be possible to build self-stabilizing warp geometries, where the curvature of space-time automatically adjusts to preserve balance, a sort of cosmic autopilot for the bubble's integrity. Others have speculated that quantum effects might, under certain conditions, help maintain stability rather than destroy it. But so far, these ideas exist only in abstract models and speculative mathematics, far removed from anything that could be tested or engineered. If we step back for a moment, The sheer delicacy of the warp bubble reveals something profound about the nature of our universe. It's not that space-time can't be bent. We see that happen naturally around stars, planets, and black holes. It's that bending it in a controlled, sustained, and directed way is like trying to sculpt a storm. The moment you impose order, chaos pushes back. In the case of a warp drive, the forces involved aren't just mechanical or thermal. They're gravitational and quantum, woven into the very foundation of reality. So even in the most optimistic scenario, where we could produce exotic matter and shape it into the right configuration, the warp bubble might still be too unstable to survive more than a few moments. It could flicker into existence, shimmer briefly like a mirage, and then vanish, taking whatever was inside it with it. And that's assuming it could form safely at all. The stability issue then isn't just a technical challenge. It may represent a fundamental limitation of physics itself. It's possible that the universe simply doesn't permit macroscopic regions of superluminal curvature to persist, no matter how clever our equations are. Yet even this hasn't stopped physicists from exploring further. Because beyond the problem of keeping the warp bubble stable lies an even stranger and potentially more troubling issue, one that threatens the very consistency of cause and effect. If we could somehow ride a warp bubble across space faster than light, would we also be traveling backward in time? If the stability issue wasn't enough to make physicists uneasy, the next consequence of warp travel dives into even stranger and more unsettling territory: causality. This is the principle that underpins all of physics. That cause precedes effect. That every event follows logically from another. It's what ensures that time moves forward, that broken glass doesn't reassemble itself, and that you can't read a message before it's written. Yet, the moment faster than light FTL travel enters the equation, causality begins to unravel. And with warp drives, which effectively allow you to cross vast distances faster than light would in normal space, that unraveling becomes a very real theoretical problem. The issue arises directly from Einstein's own relativity. According to the theory, time and space aren't separate entities. They're part of a single fabric called spacetime. The faster you move through space, the slower you move through time relative to other observers. This relationship is what gives rise to time dilation, the famous twin paradox, where a twin traveling near light speed returns younger than their sibling who stayed on Earth. Now, if an object could somehow travel faster than light, the equations of relativity predict something even stranger. From some reference frames, that object wouldn't just be moving faster. It would appear to be moving backward in time. This isn't science fiction. It's a direct mathematical consequence of how space-time works. If two observers are in different locations and one uses FTL travel to send a signal or move between them, relativity says that in at least one of them, those observers' frames of reference, the sequence of events could reverse. The traveler could arrive before they left. This creates the classic causality paradox, a situation where cause and effect can loop on themselves, allowing for all the famous paradoxes that haunt time travel stories. Killing your own grandfather before you're born, receiving a message you never sent, or changing an event that should have already happened. The Alcubierre warp drive, though still technically operating within general relativity, doesn't escape this issue. Because the warp bubble effectively allows information or matter to travel between two distant points faster than light would through normal space, it opens the door to frames of reference where the order of events gets scrambled. Physicists like Alan Everett and Ken Olum have analysed Alcubierre's model and shown that if you could create two warp bubbles moving in opposite directions, it would be possible to construct a closed time-like curve, a path through space-time that loops back on itself. In simple terms, This would make time travel to the past possible. At first glance, that might sound thrilling, a potential byproduct of warp technology that would let us visit the past or change history. But for physics, it's a nightmare. Time loops break the self-consistency of the universe. If cause and effect can be reversed, the entire logical structure of physical law collapses. For instance, if you could prevent the event that caused your journey in the first place, then your trip could never occur, and yet it already did. These contradictions are not just philosophical headaches, they're direct violations of the mathematical and logical coherence of space-time itself. Physicists refer to this as the chronology protection problem. Stephen Hawking famously argued that the laws of physics conspire to prevent time travel on a macroscopic scale. In other words, even if general relativity allows for solutions like warp drives and wormholes that could lead to backward time travel, quantum effects or other mechanisms would likely intervene to stop them from becoming physically real. Space and time, in Hawking's view, have built-in safeguards to preserve causality, though no one knows exactly how these safeguards work. It's possible that the moment you try to create a region of space-time capable of violating causality, some quantum instability or feedback effect would destroy it instantly. In the case of the Alcubierre drive, such a chronology protection mechanism might manifest as catastrophic instability in the warp bubble, exactly the kind of spontaneous collapse that other researchers have predicted. It's as if the universe itself refuses to allow information to move backward in time, and any attempt to do so triggers a kind of self-destruct. Whether this is an inevitable law or just a quirk of our current understanding of physics remains one of the deepest open questions in cosmology. The causality problem does more than threaten our concept of time. It challenges the very idea of predictability. Physics, at its core, is about being able to say, given certain conditions, this will happen next. If those cause and effect chains can loop back on themselves, prediction becomes meaningless. The universe becomes inconsistent, where past, present, and future can no longer be neatly separated. It's the ultimate paradox, and one that most physicists believe nature will never allow. And yet, despite these potential contradictions, the exploration of warp drives continues to push our understanding of space and time further. It forces us to question what impossible really means. Perhaps the laws of physics won't allow us to break causality, but that doesn't mean the journey to understand why won't reveal something extraordinary about the structure of reality itself. Still, even if time paradoxes could somehow be avoided, another challenge awaits any hypothetical warp traveler, one that's not philosophical but deadly. Because as a ship approaches light speed or creates a warp bubble, it wouldn't just bend space-time. It would also trap something far more dangerous: radiation. Even if humanity somehow managed to overcome the near-impossible energy requirements, the instability issues, and the terrifying implications of causality violations, there's yet another deadly problem lurking in the heart of warp physics: radiation. In the real universe, faster-than-light travel isn't just a theoretical or temporal hazard, it's a physical one. A ship moving at relativistic speeds or enveloped within a warp bubble would face an onslaught of high-energy particles and radiation so intense that it could annihilate everything on board, and quite possibly everything around it when the bubble collapses. To understand why, imagine what happens to a spacecraft moving close to the speed of light through interstellar space. Even though the vacuum of space seems empty, it's filled with stray hydrogen atoms, cosmic rays, and interstellar dust. At ordinary speeds, these particles are harmless, tiny motes of matter floating through the void. But as a ship accelerates toward light speed, the relative energy of those particles skyrockets. To the ship, each atom becomes a high-energy bullet, carrying lethal radiation levels equivalent to particle beams from a particle accelerator. At 99.999% of light speed, a single hydrogen atom could hit the ship's hull with the energy of a small explosive. Now imagine encountering millions of those every second. In a warp drive scenario, the situation becomes even more extreme. The Alcubierre drive doesn't move the ship through space, but it does manipulate space-time itself, creating a distortion that would drag along interstellar particles, radiation, and electromagnetic energy. As the warp bubble travels, it would act like a massive cosmic plow, compressing and accumulating energy at its leading edge. Every stray particle, every photon, and every quantum fluctuation in its path would be swept up and trapped within the bubble's boundary. This energy wouldn't just disappear, it would build up, compressed into higher and higher frequencies as the bubble moved faster. Physicists like Brendan McMonagall and William Erickson have modeled what this would mean in practice, and the results are terrifying. They found that any warp bubble traveling faster than light would accumulate enormous amounts of high-energy radiation, from X-rays to gamma rays, at its front edge. The longer the journey and the faster the bubble, the greater the buildup. The ship inside the bubble might be safe during the trip, shielded from this radiation by the bubble's geometry. But the danger comes when the warp field collapses. When that bubble finally dissipates, whether intentionally or due to instability, all the trapped radiation and high-energy particles would be released in an instant. The result would be a massive burst of destructive energy, essentially a cosmic explosion. The calculations suggest that even a small warp bubble, moving faster than light for just a short distance, could unleash enough radiation upon collapse to sterilize everything in its immediate vicinity, possibly even vaporize entire planets if it re-entered normal space near one. It would be like releasing the energy of a supernova compressed into a single moment. This radiation burst problem creates a chilling paradox. The warp bubble, meant to carry travelers safely across the cosmos, would become a weapon of unimaginable power upon arrival. Any civilization capable of creating one would need to carefully manage not only the immense energy needed to form the bubble, but also the catastrophic energy it would discharge at the end of its journey. It's possible that even if a warp drive could function, no one would ever dare to use it near any inhabited world. There's also a more subtle issue that compounds the danger: blue shifting. As the bubble moves through space, light waves from stars ahead of it would be compressed into increasingly higher frequencies, shifting into deadly gamma rays. Even before the bubble collapses, the front edge would effectively become a wall of radiation, making navigation toward any luminous object, like a star or planet, incredibly hazardous. In a very real sense, the faster the warp bubble moves, the more destructive it becomes. And this doesn't even take into account quantum effects. Some theories suggest that at superluminal speeds, the warp bubble might generate Hawking-like radiation, similar to what's predicted near black holes. This would occur because the bubble's boundaries act as event horizons, separating regions of space-time in such a way that virtual particles could become real, spewing radiation into the bubble. If true, the interior of the warp field might slowly fill with lethal levels of high-energy particles, cooking any occupants long before the journey ends. So, while the warp bubble may solve the problem of speed, it introduces a new kind of peril, one rooted in the very structure of space-time and the energy it carries. Every photon, every atom, every quantum ripple becomes a potential source of annihilation. It's not just a matter of shielding or engineering. This is a fundamental consequence of how energy behaves under extreme curvature. For all these reasons, even the most optimistic physicists admit that warp travel, as currently understood, might be too dangerous to ever use. A single miscalculation, an unanticipated radiation buildup, or a premature bubble collapse could turn a voyage into a cosmic disaster. But even beyond the physical dangers, there's another barrier that keeps warp drives in the realm of theory. One that's not about energy or radiation, but about computation. To even simulate how a warp bubble behaves, let alone control it, would require calculating the dynamics of spacetime on scales far beyond what any supercomputer can handle today. The next challenge isn't just about building the drive. It's about understanding it at all. Even if humanity had the energy, the exotic matter, and the perfect engineering precision to construct a warp bubble, there remains a subtler, yet equally daunting challenge that stands in the way: the limits of our computational understanding. Before we can ever hope to build a warp drive, we have to be able to simulate one. And that, as it turns out, might be one of the most computationally demanding problems in the history of science. The equations governing the Alcubierre drive come directly from Einstein's field equations, a set of 10 interlinked, non-linear differential equations that describe how matter and energy curve spacetime. These equations are famously difficult to solve, even for simple systems like two orbiting black holes. To model a dynamic warp bubble, physicists must not only solve these equations, but also simulate how spacetime continuously distorts, expands, and contracts in response to constantly changing energy densities, including negative ones. That's not just a math problem, it's a computational nightmare. Every warp bubble scenario involves extreme spacetime geometries, regions where curvature changes rapidly across incredibly small distances. To simulate those conditions accurately, computers need to break spacetime down into billions or trillions of tiny units, running vast numerical calculations for each, step by step. Even the most powerful supercomputers in the world today struggle with these types of computations when modeling phenomena like merging black holes, and a warp bubble is orders of magnitude more complex. To make things harder, negative energy doesn't behave like normal matter or radiation in these models. It has repulsive gravitational properties, and its interactions with normal spacetime curvature are poorly understood. When physicists try to simulate it, small numerical errors tend to blow up exponentially, crashing the entire model. In computational physics, this is called instability in the solution, and it's one reason we can only simulate very limited versions of warp spacetime. Most models simplify or freeze parts of the geometry, focusing on static snapshots instead of fully dynamic, evolving bubbles. Recent attempts to simulate warp drives, such as those by Jose Notario, Harold White, and others, have used clever approximations to make the problem more manageable. Instead of trying to calculate the full 4D spacetime geometry, they focus on simplified slices that represent how the curvature might behave under certain assumptions. Even then, the computational load is immense. A complete simulation that included quantum effects, gravitational feedback, and the behavior of matter inside and outside the bubble would require computational power far beyond anything we currently possess, possibly even beyond the theoretical limits of conventional computing. Some researchers believe that quantum computing might one day help with this. Because quantum computers can handle multiple states simultaneously, they might be uniquely suited to modeling the non-linear, probabilistic behavior of spacetime on quantum scales. But even if that's true, we're still decades, perhaps centuries, away from quantum computers powerful enough to simulate something as vast and intricate as a warp field. The deeper issue is that we don't yet fully understand how general relativity and quantum mechanics interact at the extremes required for warp dynamics. Our equations break down near the Planck scale, where spacetime becomes quantized and turbulent. In that regime, gravity is no longer smooth and continuous. It fluctuates violently, and our models simply stop working. To truly simulate a warp bubble, we'd need a theory of quantum gravity, a framework that unites relativity and quantum physics into a single, consistent description of reality. Without that, our computer models are like trying to simulate the ocean while ignoring the existence of water molecules. Even on a practical level, the control systems for a real warp drive would have to process unimaginable amounts of data in real time. The curvature of spacetime would need constant monitoring and correction to prevent collapse or runaway instability. Every fluctuation in the energy field, every minor variation in the vacuum structure, could cause catastrophic failure. Controlling such a device might require an artificial intelligence capable of analyzing and adjusting spacetime geometry on femtosecond timescales, far beyond the limits of any technology we can currently imagine. This computational barrier highlights an often overlooked truth. Before humanity can even attempt to build a warp drive, we must first learn to fully simulate and understand one. And that means we need not only better hardware, but also a deeper, more unified theory of how the universe works at its most fundamental level. But progress, even slow progress, is happening. Researchers at institutions like NASA's EagleWorks, the University of Göttingen, and independent groups worldwide are developing refined mathematical models that test the limits of our computational tools. Each simulation, no matter how simplified, teaches us a little more about what's possible, what's forbidden, and where our current physics might one day give way to something new. So while today's computers can barely begin to model warp spacetime, every iteration brings us closer to understanding how reality behaves when pushed to its extremes. And as that understanding deepens, so too does the hope that maybe, just maybe, there's a path forward. Indeed, some scientists are already taking tentative steps beyond the purely theoretical, searching for physical warp fields that might exist within the boundaries of known physics. A modern reimagining of Alcubierre's dream, built from the faint but growing sparks of experimental and computational progress. In recent years, a quiet but determined group of scientists has continued to chip away at the theoretical walls surrounding the idea of warp drives. While the dream of building an Alcubierre-style engine remains far beyond our reach, new research has begun to transform that dream from pure fantasy into a more grounded field of scientific inquiry. Physicists today are no longer simply asking, "Can we do it?" They're asking, "How close can we get without breaking the laws of physics?" One of the most promising areas of study focuses on reducing the energy requirements of the original Alcubierre model. When Miguel Alcubierre first proposed his drive in 1994, the energy needed to form a single warp bubble was so vast that it exceeded the mass energy of the observable universe. But over the decades, refinements to his equations have shown that those astronomical numbers might be drastically reduced through clever geometrical modifications. In 1999, physicist Chris van den Broek proposed a significant reworking of the Alcubierre metric. By shrinking the volume inside the warp bubble, where the ship would sit, and increasing the size of the surrounding warp field, Van den Broek showed that the total energy requirement could theoretically be reduced from universal scales to something closer to the mass of a large planet, or even a few kilograms of matter. While still well beyond our current capabilities, this breakthrough proved something crucial. The warp drive wasn't completely off the table. It might not require infinite energy after all, just enormous amounts. This sparked renewed interest among researchers, looking for even more efficient space-time configurations. In the 2000s, Harold "Sonny" White, a physicist at NASA's EagleWorks laboratory, began exploring what he called modified Alcubierre geometries. Using refined versions of the original equations and computer modeling, he suggested that by changing the shape of the warp bubble from a sphere to a more toroidal, donut-like form, the energy demands might be further reduced, perhaps down to the energy equivalent of a few metric tons of matter. White's experiments with a device known as the White-Juday interferometer sought to detect microscopic distortions in spacetime, hinting at the possibility of generating tiny, measurable warp fields in the lab. Although his results were controversial and far from conclusive, they demonstrated a shift in how seriously this area of research was being taken. What had once been a topic confined to science fiction conventions was now being cautiously examined by real physicists in professional settings. In 2021, a particularly exciting development emerged when a team at the Limitless Space Institute, a research organization dedicated to studying advanced propulsion concepts, claimed to have discovered a theoretical configuration resembling a nanoscale warp bubble. While this was purely mathematical, it showed that under certain quantum field configurations, a small region of space could mimic the geometry of Alcubierre's warp metric without violating known physics. This finding didn't mean we could suddenly build a warp engine, but it provided a crucial proof of concept that such space-time structures could, in theory, exist naturally within quantum fields. Other studies have shifted focus toward creating physical warp drives, theoretical constructs that obey all the known energy conditions of general relativity, meaning they wouldn't require exotic matter at all. One of the most notable efforts came from a 2021 paper by Alexei Bobrik and Gianni Martiri, who proposed a new class of subluminal warp drives. These configurations wouldn't allow faster-than-light travel, but could still manipulate spacetime to create gravitational propulsion effects within the limits of relativity. Their work suggested that with the right mass-energy distribution, it might be possible to generate a warp-like motion where space expands behind a ship and contracts in front, just not fast enough to break the light barrier. This concept of a physical warp drive represents a shift from wild speculation toward realistic experimentation. It implies that, while superluminal travel remains beyond our grasp, controlled spacetime curvature might one day allow for new propulsion methods, perhaps letting ships surf gravitational gradients or reduce inertia during acceleration. Essentially, these studies keep the spirit of Alcubierre's vision alive while grounding it more firmly in the physics we understand today. And it's not just theoretical. Some research groups have begun exploring laboratory analogues, small-scale systems that imitate aspects of space-time curvature using electromagnetic fields, metamaterials, or laser interferometry. These analog models can't create real warp bubbles, but they allow scientists to test how energy distributions affect curvature-like effects in controlled conditions. Such experiments might one day help us understand how spacetime responds to concentrated fields, bringing us one step closer to controlled spacetime engineering. Despite all this progress, it's important to keep perspective. These breakthroughs are still baby steps. Mathematical rearrangements, computational models, and laboratory approximations. We're nowhere near a functioning drive. But what's significant is that warp research has transitioned from pure speculation to an active area of theoretical physics. Scientists are refining the equations, testing the limits, and discovering where reality begins to resist our imagination. In that process, we're learning more than just whether a warp drive is possible. We're uncovering new insights into the nature of gravity, quantum fields, and the structure of spacetime itself. Each discovery, even the small ones, expands our understanding of how flexible the universe truly is. And while no one expects a Starship Enterprise to launch anytime soon, the continued study of warp physics is quietly building the foundation for whatever comes next. Because as remarkable as these refinements are, there's still a deeper frontier left unexplored, one that lies at the intersection of Einstein's smooth, geometric universe and the jittery quantum world beneath it. The next step in our journey brings us to the biggest missing piece of all, the search for a theory of quantum gravity, the key that might finally show how space-time can truly be controlled. While warp drives still live in the realm of theory, The fascination they inspire has spilled beyond university whiteboards and science fiction discussions into real research environments. Over the past 2 decades, a handful of organizations, labs, and independent physicists have begun to explore warp physics with a cautious but genuine scientific curiosity. These groups aren't building starships, not yet, but they're probing the limits of relativity, quantum field theory, and advanced propulsion concepts in search of small, measurable steps toward what once seemed purely impossible. Among the most recognized of these efforts is NASA's EagleWorks laboratory, founded and led for several years by Dr. Harold "Sonny" White. Based at NASA's Johnson Space Center, EagleWorks was established to explore breakthrough propulsion ideas, everything from the EM drive to warp field mechanics, in a serious, structured environment. White's work focused heavily on refining the original Alcubierre metric, looking for ways to make warp fields energy efficient enough to be physically conceivable. His theoretical papers proposed modifications to the shape and distribution of the warp bubble that could reduce the required negative energy from universe-sized amounts to something more manageable, perhaps the mass energy equivalent of a few hundred kilograms. EagleWorks even attempted laboratory-scale experiments. Using a highly sensitive device called the White-Juday interferometer, the team sought to detect minute distortions in space-time that could indicate the presence of a tiny, localized warp field. While no definitive warp signature was ever observed, these experiments were valuable for pushing the boundaries of precision measurement and inspiring new methods for probing gravitational and electromagnetic interactions at microscopic scales. For NASA, EagleWorks represented an acknowledgement that even highly speculative ideas deserve rigorous testing. Not to build a warp drive tomorrow, but to ensure we don't overlook something revolutionary hiding within the equations of physics today. Outside of NASA, independent and private groups have also joined the pursuit. One of the most active is the Limitless Space Institute, LSI, founded in part by Sonny White after leaving NASA. The organization's goal is to inspire and educate the next generation to travel beyond our solar system by funding advanced propulsion research. LSI collaborates with universities and private researchers worldwide, focusing on concepts such as warp metrics, quantum vacuum manipulation, and energy-efficient space-time geometries. In 2021, White and his LSI team made headlines after publishing a paper describing a nanoscale warp bubble, not a functioning drive, but a theoretical structure discovered during energy density modeling for a Casimir cavity experiment. The geometry they found, remarkably, matched the mathematical profile of a real Alcubierre-like bubble, albeit on an unimaginably small scale, perhaps nanometers across. While this doesn't mean warp drives exist, it was the first time anyone had derived such a geometry accidentally from realistic physical conditions, hinting that space-time might naturally allow such configurations in the quantum realm. Another significant contributor to warp research is applied physics, an independent team of theoretical physicists and engineers that published several influential papers between 2020 and 2023. Led by Alexei Bobrik and Gianni Martire, they developed models for physical warp drives, theoretical space-time metrics that obey all known energy conditions, meaning they don't require negative energy or exotic matter. Their 2021 paper in Classical and Quantum Gravity introduced the concept of a subluminal warp drive, a space-time configuration that could manipulate gravitational curvature to create motion effects similar to Alcubierre's drive, but without breaking the speed of light or the laws of physics. These solutions don't promise interstellar travel yet, but they suggest that controllable space-time engineering could be possible in principle, even within the limits of known physics. Meanwhile, at universities and think tanks across the world, Smaller teams and independent researchers continue exploring warp physics from different angles. Some study quantum field effects that might one day produce stable negative energy densities. Others are working on numerical relativity simulations that model how warp bubbles might behave under various conditions. And a few brave theorists continue to probe the limits of Einstein's equations, searching for new warp metrics that minimize energy, maintain stability, and preserve causality. These researchers, often working without funding or institutional support, represent the true spirit of exploration that drives the field forward. The very existence of these organizations and studies marks a profound shift in how science views speculative propulsion. For most of the 20th century, topics like warp drives, wormholes, or anti-gravity were dismissed as pseudoscience. But today, they're recognized, cautiously, as valid theoretical explorations of general relativity and quantum field theory. NASA's involvement, the publications in peer-reviewed journals, and the computational models being run on high-performance machines all testify to the fact that warp physics has entered the fringes of legitimate research. Of course, even the most optimistic researchers admit that a functioning warp drive is likely centuries away, if it's possible at all. These organizations aren't promising interstellar voyages, they're probing the edges of the possible. By doing so, they not only advance our understanding of space-time, but also help refine technologies that might one day lead to new breakthroughs in energy, propulsion, and quantum science. Still, one enormous piece of the puzzle remains missing: a bridge between the worlds of relativity and quantum mechanics. The deeper we explore warp physics, the clearer it becomes that our current understanding of gravity isn't enough. The next step may depend on solving one of the most profound mysteries in all of science: how to unite Einstein's smooth, continuous space-time with the chaotic, probabilistic world of quantum physics. Only then might we discover whether warp drives can move from mathematics to machinery. At the very core of all our struggles to understand, and possibly one day build, a warp drive lies a fundamental truth: our picture of the universe is still incomplete. Physics today is built on two great pillars: Einstein's general relativity and quantum mechanics. And while each works brilliantly in its own domain, they simply refuse to cooperate when brought together. This incompatibility sits at the heart of why warp drives remain firmly theoretical. Because to truly bend, stretch, and move space-time as the Alcubierre model demands, we would need to manipulate gravity and energy at scales where both theories collide. And right now, we don't have the mathematics or the physics to describe that region of reality. General relativity treats the universe as a smooth, continuous fabric of space-time, shaped by the distribution of matter and energy. It works spectacularly well for describing planets, stars, black holes, and the large-scale structure of the cosmos. But as powerful as it is, relativity breaks down when we peer too closely. At the quantum level, where space-time isn't smooth at all, but instead flickers and fluctuates like a stormy sea of probabilities. Quantum mechanics, on the other hand, governs that microscopic world of particles, energy quanta, and fields, a realm where uncertainty and probability rule. It explains everything from the behavior of electrons to the structure of atoms and the weirdness of entanglement. Yet, it says nothing coherent about gravity. The trouble begins when you try to make these two frameworks talk to each other. In relativity, gravity is geometry, a curvature of space-time caused by mass and energy. In quantum theory, all forces are mediated by particles, tiny quanta that exchange energy in discrete packets. So, if gravity were like the other forces, it too should have a quantum particle, the hypothetical graviton. But every attempt to combine these ideas leads to mathematical chaos. Infinite energies, nonsensical results and equations that refuse to balance. It's as if the universe is whispering, "You're close, but not quite there yet." This missing piece, the theory of quantum gravity, is what many physicists believe we need before concepts like the warp drive can become physically meaningful. Because a warp bubble isn't just a gentle curve in space-time, it's an extreme distortion where the geometry of the universe itself is twisted into unnatural shapes. At those levels of curvature and energy density, quantum effects can't be ignored. Virtual particles, vacuum fluctuations, and zero-point energy, all the wild phenomena of quantum physics, begin to interact directly with space-time curvature. Without a theory that unites these two realms, we're trying to describe half the story with two incompatible languages. Some of the most advanced attempts to develop quantum gravity, such as string theory, loop quantum gravity, and causal dynamical triangulations, might eventually provide the tools to understand what's really happening inside a warp bubble. In string theory, for instance, space-time and gravity emerge naturally from the vibrations of tiny, fundamental strings. This framework suggests that space-time isn't truly continuous, but quantized at incredibly small scales, like pixels in a cosmic simulation. If that's true, then perhaps space-time could be reprogrammed or manipulated in precise ways, a necessary step toward controlled curvature and warp propulsion. Loop quantum gravity, meanwhile, proposes that space itself is woven from discrete loops of gravitational fields, forming a granular, dynamic network. In that view, bending space-time might involve rearranging its fundamental structure, not just applying massive amounts of energy. These ideas are still deeply speculative, but they point toward an important insight. A true warp drive may not just be a feat of engineering. It might require a new kind of physics altogether. To manipulate space-time on command, we'd have to understand its quantum structure, learn how energy and gravity interplay at their deepest level, and possibly discover new forms of matter or energy that don't yet exist in our equations. Without that unified theory, our current models, even the beautifully elegant ones like Alcubierre's, remain incomplete approximations, unable to account for the quantum-level effects that would dominate any real warp field. Another reason quantum gravity matters so profoundly is that it could resolve the paradoxes we've already encountered: the instability of the warp bubble, the causality violations, and the radiation buildup. These phenomena all arise because our classical understanding of space-time breaks down under extreme conditions. A working quantum gravity theory could, in principle, tell us whether those problems are fundamental, written into the fabric of reality, or simply artifacts of our incomplete models. It might reveal hidden mechanisms that stabilize space-time distortions or provide natural limits that prevent paradoxes. Until then, every discussion about warp drives remains a balancing act on the knife's edge between two incompatible theories. We can calculate, model, and dream, but we're still missing the one framework that could tell us if those dreams are even possible. The universe may already have the rules for warp travel built into its deepest structure. We just haven't deciphered them yet. And even if we do someday crack the code of quantum gravity, another monumental challenge awaits: power. The energy required to shape space-time, even with a perfect understanding of physics, is still staggering beyond measure. To move a ship faster than light, we would need to harness energy sources far beyond anything humanity has ever achieved, from fusion and antimatter to perhaps even the energy of black holes themselves. Understanding the universe is one thing. Powering our way through it is quite another. Even if we somehow discovered the physics necessary to manipulate space-time, one obstacle would still stand tall like a cosmic wall: power. The energy needed to bend space and time, even in the most optimistic warp drive models, dwarfs anything our species could currently produce, or even dream of producing. To warp space-time, you're not just moving matter, you're distorting the very geometry of the universe itself, commanding the gravitational forces that usually only black holes and supernovas can muster. And despite all our technological progress, from nuclear fission to antimatter research, our ability to generate, store, and control energy remains orders of magnitude too weak for warp-level demands. Let's start with what we already have: fusion, the process that powers the sun. Fusion merges atomic nuclei together, releasing enormous amounts of energy relative to chemical fuels. If you could harness the energy produced by fusing hydrogen into helium, a single kilogram of fuel could release as much energy as burning millions of kilograms of coal. Humanity has pursued controlled fusion for decades, and we've finally begun to see glimpses of success with experimental reactors like ITER and the National Ignition Facility. But even if we perfected fusion tomorrow, it would still be hopelessly insufficient for warp drive purposes. The energy output of our best fusion designs would barely scratch the surface of what's required to warp even a few meters of spacetime. So what about antimatter, the most efficient energy source known to physics? When matter and antimatter collide, they annihilate completely, converting their entire mass into pure energy. A few grams of antimatter could, in theory, release as much energy as thousands of nuclear bombs. On paper, this looks promising, but in practice, it's nearly useless for warp propulsion. For one, creating antimatter takes enormous amounts of energy in the first place. The world's most advanced particle accelerators, such as CERN, can produce only a handful of nanograms of antimatter per year, and at astronomical costs. Even if we could generate and safely store it, which itself is a huge challenge since antimatter destroys any normal matter it touches, the total amount needed for a warp bubble would be beyond comprehension. To put it into perspective, the antimatter equivalent of mountains of mass would be required just to form the smallest space-time distortion predicted by Alcubierre's model. Then there's the most exotic idea of all: extracting energy from black holes. Theoretically, rotating black holes contain enormous amounts of energy trapped in their spinning space-time, and some physicists have proposed ways to tap into it through what's known as the Penrose process or Hawking radiation. In essence, it's the ultimate cosmic battery, the conversion of the gravitational and rotational energy of a black hole into usable power. If humanity ever mastered such a technique, it could provide energy on galactic scales. Yet even then, the sheer magnitude of what's needed for warp propulsion would remain staggering. The energy required to bend space-time into a usable warp bubble, even by the most reduced estimates, could equal the total output of entire stars, sustained not for seconds or minutes, but continuously, to maintain the bubble's stability and motion. To make matters more difficult, the energy wouldn't just need to exist, it would have to be controlled. Unlike burning fuel or releasing heat, creating a warp field requires energy distributed in extremely specific ways, concentrated into precise regions of positive and negative density that must balance perfectly across the bubble. This kind of controlled energy shaping, directing pure power to sculpt space-time itself, is beyond any technology we can currently conceive. We can't even maintain stable magnetic fields at small scales without imperfections or instabilities, let alone stabilize the energy geometry of the universe. Some scientists have suggested that one day we might draw power from more speculative sources, like the zero-point energy of the quantum vacuum, the energy that exists even in empty space. Quantum theory tells us that even a perfect vacuum seethes with tiny fluctuations, virtual particles appearing and vanishing constantly. Theoretically, if we could tap into that energy, it would provide an infinite supply of power. But so far, it's just that, theoretical. We have no way to extract vacuum energy, And most physicists suspect that the universe itself may forbid it, since doing so would destabilize space-time. All of this underscores a humbling truth. Even if the physics of warp travel one day prove valid, the engineering of power might still be the real barrier. Our entire global civilization, every reactor, every generator, every solar panel combined, produces only a tiny fraction of the energy needed to even begin forming a warp field. To reach the necessary levels, we'd need power systems capable of harnessing forces equivalent to the output of stars, sustained indefinitely, with precision fine enough to manipulate space-time geometry. In that light, the problem of energy generation isn't just technological, it's existential. It highlights how small we still are in the face of cosmic power. Yet, it also points toward what the future might demand of us. New energy paradigms, new ways of interacting with the universe. Perhaps someday, when we've mastered fusion or learned to control quantum vacuum fluctuations, we'll find the first glimpses of the kind of power warp travel needs. But even if that day comes, energy alone won't be enough. Creating a warp drive wouldn't just mean finding power. It would mean engineering the impossible. The materials, the structure, the feedback systems, the shielding, every component would have to withstand conditions at the very limits of physics. And that brings us to perhaps the most daunting obstacle of all: the sheer engineering impossibility of building a machine capable of reshaping space-time itself. Even if the universe were to hand us the keys to its deepest physical secrets, the equations for quantum gravity, the recipe for negative energy, and a limitless power source, we would still face a seemingly insurmountable challenge: actually building a warp drive. Because even if the physics one day works, the engineering almost certainly won't. The sheer complexity of constructing a machine capable of bending space-time on command is so staggering that it borders on the unimaginable. We are not just talking about pushing materials or machines to their limits. We are talking about creating an object that would operate at the very edge of reality itself. At its core, a warp drive is not a machine in the traditional sense. It's a space-time geometry, a bubble of distorted reality that surrounds a spacecraft. To make that geometry real, we'd need to control gravity with surgical precision. Every point in the warp field would require exact energy densities and space-time curvatures. Any imbalance could make the bubble collapse, twist uncontrollably, or generate lethal tidal forces. We are nowhere near being able to measure, let alone manipulate, such fine curvature of space-time. Our most sensitive instruments today, devices like LIGO, which detect gravitational waves from merging black holes, can measure distortions in space-time that are smaller than a proton's width. That's an extraordinary achievement, but even that level of precision is billions of times less than what a warp drive would require for real-time control. Then there's the matter of materials. The environment around a warp bubble would be unlike anything found in nature. On one side, space would be compressed and warped inward. On the other, it would be stretched outward. Enormous gravitational gradients would ripple across the boundary of the bubble, gradients that could shred atoms apart, distort molecular bonds, and vaporize any conventional structure. The hull of a warp-capable ship would need to withstand forces equivalent to those found near neutron stars, all while maintaining perfect symmetry and balance. No known material, not even the most exotic theoretical constructs like carbon nanotubes or metallic hydrogen, could survive such conditions. In fact, the very concept of a hull might be meaningless. The structure would have to be integrated into the warp field itself, functioning less like a physical shell and more like a self-stabilizing space-time region. And even if we could build materials that could survive those forces, how would we control the field? The warp bubble's stability would depend on continuous feedback. an active adjustment of space-time curvature in response to internal and external fluctuations. It would require sensors capable of detecting minute distortions in space-time faster than the speed of light and actuators capable of correcting them instantly. That's not just beyond our current technology, it's beyond causality. No signal, not even light, can travel fast enough to regulate a warp bubble from within, meaning any control system we designed would already be too slow. Shielding is another problem. The bubble itself might protect the ship from the direct effects of relativistic motion, but the boundary of the warp field could accumulate lethal radiation and high-energy particles, as mentioned earlier. To protect the crew, the ship would need to deflect or dissipate this energy somehow, possibly by redirecting it into other regions of space-time. But that would require manipulating gravitational and electromagnetic fields with precision that boggles the mind. The slightest failure in shielding could bathe the ship's interior in deadly gamma radiation or collapse the field entirely. Even communication and navigation pose unique challenges. A ship inside a warp bubble would be completely isolated from the outside universe. Signals, light, and even causal information couldn't pass through the warp field boundary. That means no messages to or from the ship while in warp, no steering corrections, and no real-time control. The crew would essentially be sealed in a self-contained pocket of space-time, unable to interact with the universe until the bubble collapsed. Navigation would have to be pre-programmed with near-perfect accuracy. One wrong calculation, and the ship could emerge light years from its target, or worse, inside a star, a black hole, or deep intergalactic space. Then there's the problem of initiating the warp bubble. To start the drive, you'd need to create a region of space-time with the right geometry and energy density, a process that might require conditions rivaling those at the beginning of the universe. How would you even begin to do that from a standing start? The paradox of warp drive engineering is that it might take a warp-capable infrastructure to build one in the first place, a chicken and egg problem of cosmic proportions. In many ways, these engineering barriers highlight a profound philosophical question. Even if something is physically possible, does that mean it's achievable? The warp drive may sit in the narrow space between physical law and practical impossibility, theoretically allowed by the equations, but forever out of reach due to the sheer scale and precision it demands. And yet, the act of studying these impossibilities often leads to progress. Technologies we take for granted today, GPS, nuclear energy, quantum computing, all trace their roots to theoretical questions that once seemed absurd. It's possible that warp drive engineering will never exist in any form we can currently imagine. But it's also possible that the principles behind it, the manipulation of space-time curvature, the control of energy density, the shaping of gravity, could lead to more achievable technologies. Maybe one day we won't travel through space at warp speed, but we'll use the same ideas to revolutionize energy storage, propulsion, or even communication. And while warp drives may remain a dream for now, they're not the only idea humanity has for beating the light speed limit. Physicists have long speculated about other faster-than-light concepts, from wormholes to tachyons to quantum tunneling, each offering its own strange loophole in the cosmic rulebook. Yet, like the warp drive, all of them run headfirst into the same unyielding barriers of physics, energy, and causality. When people dream about breaking the light speed barrier, warp drives are only one piece of a much larger puzzle. Over the decades, physicists and dreamers alike have proposed several other methods to traverse the vastness of space faster than light. Wormholes, tachyons, and quantum tunneling among them. Each of these ideas offers its own kind of shortcut through the universe. Yet, when examined closely, all of them run into the same walls of physics that keep warp drives trapped in the realm of theory. They may approach the problem differently, But their limits, energy, stability, causality, and quantum constraints, are strikingly familiar. The most famous alternative is the wormhole, sometimes called an Einstein-Rosen bridge. Unlike a warp bubble, which distorts space locally to move a ship from one point to another, a wormhole connects two distant regions of spacetime directly through a tunnel-like structure. Imagine folding a sheet of paper so that two distant points touch. That's essentially what a wormhole does to the universe. In theory, you could enter one mouth of the wormhole, travel through its interior, and emerge instantly at the other end, no matter how far apart those points are. It's not moving faster than light in a conventional sense. You're just taking a cosmic shortcut. Einstein and his collaborator Nathan Rosen first described wormholes in 1935. But it was physicist Kip Thorne and his colleagues in the late 20th century who explored whether such structures could actually be traversable. The problem, as with the warp drive, is that wormholes require exotic matter, regions of negative energy density, to keep them stable. Without it, the immense gravitational forces at the wormhole's throat would cause it to collapse instantly. Even if exotic matter could exist, there's no known way to produce or control it on the necessary scale. Some studies even suggest that quantum fluctuations would tear a wormhole apart the moment anything tried to pass through it. Like the warp drive, wormholes may be allowed by the math, but nature seems determined to make them impossible in practice. Then there's the idea of tachyons, hypothetical particles that always move faster than light. Tachyons were once popular in theoretical physics because they appeared as mathematical solutions in certain quantum field equations. If they existed, they would never slow down to subluminal speeds. They'd always remain beyond light's reach. However, tachyons bring enormous problems. Their existence would violate causality, meaning they could send information backward in time, leading to paradoxes similar to those in warp travel. Worse, they would destabilize nearly every known physical system by allowing infinite energy exchanges. For these reasons, most physicists today believe tachyons are mathematical curiosities rather than real entities. Quantum tunneling offers a subtler and more mysterious form of faster-than-light behavior. In the quantum world, particles can sometimes tunnel through energy barriers they classically shouldn't be able to cross. When measured, tunneling can seem instantaneous, suggesting that something is happening faster than light. But this isn't true FTL travel. It's a probabilistic effect, not a transfer of matter or information at superluminal speeds. Quantum tunneling doesn't actually move particles through space faster than light. Instead, it exploits the uncertainty inherent in quantum systems. So while it's often cited as an example of faster-than-light phenomena, it doesn't offer a pathway for travel or communication across vast cosmic distances. Even more exotic are speculative ideas like quantum entanglement and the ER equals EPR conjecture, which proposes a deep link between entangled particles and microscopic wormholes. Entanglement allows two particles to share a quantum state, meaning that a change in one seems to affect the other instantly, no matter how far apart they are. However, as physicists like Einstein, Schrödinger, and Bell showed, entanglement can't be used to send usable information faster than light. The apparent instantaneous connection doesn't carry data. It's a correlation revealed only when measurements are compared through normal, slower-than-light communication. In every case, wormholes, tachyons, tunneling, or entanglement, nature seems to present a similar message. The universe is willing to flirt with faster-than-light effects, but it never quite lets us exploit them. Each concept teases the possibility of breaking the cosmic speed limit, only to be reined in by deeper physical laws that preserve consistency and causality. These limits may not be arbitrary. They may be part of what keeps the universe stable. If FTL travel were easy, time could unravel, causality could break, and the orderly flow of events could dissolve into chaos. And yet, exploring these ideas is not futile, quite the opposite. Each faster-than-light concept, from Alcubierre's warp bubble to Einstein's wormholes, pushes us to ask more profound questions about the structure of space-time and the ultimate rules that govern it. Even if none of these methods ever become practical, studying them helps expand our understanding of physics at its edges, where gravity, quantum fields, and geometry all converge. In that sense, warp drives and their FTL cousins are not failures of physics. They are windows into the deepest mysteries of existence. They remind us that the universe is flexible, strange, and still only partially understood. And while we may not be able to ride these ideas to the stars, the pursuit of them brings us closer to understanding why the cosmos behaves the way it does, and perhaps how we might one day bend those rules just enough to cross its vastness. For now, though, faster-than-light travel remains a dream balanced between science and imagination. But as history has shown, dreams often pave the way for discovery. And that leads us to the most important question of all. Not what's impossible today, but what might become possible tomorrow. Because while we can't yet warp across the galaxy, the future of science may still hold surprises that turn fantasy into reality. It's tempting, after exploring all the barriers to warp travel, to simply declare it impossible and walk away, to say the speed of light is final, immutable, and absolute. But history warns us against such certainty. Again and again, humanity has reached what seemed to be the edge of knowledge, only to push past it with new discoveries that reshaped our understanding of the universe. If we are to speculate about the future responsibly, we must do so with humility, not by promising that warp drives will exist, but by acknowledging that the story of science is far from over. Physics, after all, is not a finished book. It's a work in progress, and every generation adds new chapters. A century ago, the very ideas of curved space-time, black holes, and quantum uncertainty were almost unthinkable. The notion that empty space could expand, stretch, and even accelerate galaxies away from one another would have sounded absurd. Yet today, we know these things are true. The cosmos has already shown us that space-time is flexible and that the vacuum itself has energy, the same principles that warp drive theory depends on. It's not unthinkable that future discoveries could reveal ways to control these effects, however slightly. One of the most promising frontiers for such discovery lies in the study of quantum fields, the invisible fluctuating energy fields that fill all of space. Quantum field theory already suggests that the vacuum isn't truly empty, but filled with energy, what we call the zero-point field. If scientists ever find a way to manipulate or tap into these vacuum fluctuations safely, it could revolutionize energy generation and perhaps even space-time manipulation. Some speculative research already explores whether focused electromagnetic fields or certain geometries could alter local vacuum energy densities, potentially mimicking the effects of negative energy on microscopic scales. While no experiment has come close to achieving this, the possibility remains intriguing. Then there's dark energy, the mysterious force driving the accelerated expansion of the universe. We don't know what dark energy is, only that it behaves as though it exerts negative pressure on space-time. Exactly the kind of effect that could, in principle, be harnessed for something like a warp field. If future physicists uncover the nature of dark energy, they might also uncover new ways to influence the expansion and contraction of space itself. Perhaps one day, through technologies that seem alien to us now, humanity might learn to generate tiny, controlled regions of expansion, miniature versions of the same cosmic force that shaped the universe's birth. Similarly, the study of space-time topology, how space can be twisted, looped, or connected, continues to evolve. Advanced mathematics, like string theory and quantum gravity, may one day describe how space-time behaves under conditions we can barely imagine today. It's possible that hidden symmetries or undiscovered dimensions could offer new shortcuts through the universe, not by breaking the light speed limit, but by redefining what distance even means. After all, the universe itself expands faster than light. Perhaps one day we'll find a way to ride that expansion rather than fight it. It's also important to consider the timescales involved. Warp technology, if it ever becomes possible, would likely emerge centuries, perhaps millennia, in the future. The technological leaps required would dwarf every advancement since the dawn of civilization. To reach that point, humanity would need not only unprecedented mastery of physics, but also vast energy infrastructures, materials, science beyond our current imagination, and computational systems capable of modeling and controlling space-time geometry in real time. The first steps towards such a future might not involve starships at all, but small-scale experiments, quantum field manipulation, artificial gravity, or energy-efficient curvature generation. These would be the seeds of what could eventually grow into true warp engineering. Yet, it's vital to speculate responsibly. There's a difference between visionary science and wishful thinking. The warp drive, as of today, remains a mathematical construct, not a prototype waiting in some secret lab. It's an exploration of what the universe might allow, not a promise of what humanity can achieve. Still, that doesn't make the pursuit meaningless. Theoretical research into warp physics continues to deepen our understanding of energy, geometry, and cosmology. Even if warp propulsion never becomes reality, the insights gained along the way could lead to other breakthroughs in quantum computing, gravity control, or sustainable energy. Science has a way of turning dreams into discoveries, but it does so carefully, step by step. When Galileo first turned his telescope to the heavens, he couldn't have imagined that one day humans would walk on the moon. When Einstein described the bending of space-time, he couldn't have foreseen that his equations would one day help guide GPS satellites around Earth. And so, perhaps the same will be true for Alcubierre's equations. They might never propel us across the stars, but they could light the path toward deeper truths about the nature of reality. So, while the idea of a warp drive remains out of reach, it's not dead. It lives on as a symbol of our species' restless curiosity, a reminder that progress often begins with impossible dreams. As long as humanity keeps asking questions and exploring the unknown, the future will always hold surprises. And maybe, centuries from now, the word impossible will mean something very different than it does today. In the end, the dream of a warp drive, of crossing the stars faster than light, is more than a question of technology or mathematics. It's a reflection of our deepest human impulse, the desire to go beyond the horizon, to reach for what lies just out of grasp. While the warp drive remains firmly in the realm of theory, its legacy is already tangible in the way it has pushed science itself forward. By daring to ask what if, we've been forced to confront why not, and in doing so, we've learned more about the very fabric of reality than we ever would have by staying within the limits of the possible. Every obstacle that stands in the way of a warp drive, the energy requirements, the need for exotic matter, the limits of relativity, and the mysteries of quantum gravity, reveals a frontier in our understanding of physics. These are not failures, they are signposts. They show us where our knowledge ends and where the next great discoveries must begin. In wrestling with the impossible, physicists are uncovering new insights into space-time, energy, and causality. Each thought experiment, each simulation, each attempt to reconcile theory with observation brings us closer to understanding not just whether warp travel is feasible, but how the universe itself truly works. The pursuit of the warp drive also serves as a humbling reminder of our place in the cosmos. The vast distances between stars are not just barriers. They are part of the universe's design, shaping the rhythm of time and the scale of our existence. To bridge those gulfs, even in imagination, is to challenge the boundaries of reality itself. Yet in doing so, we glimpse something profound, that our curiosity, our capacity to dream of such things, is itself an extraordinary act of defiance against limitation. The laws of physics may constrain what we can do, but they cannot constrain what we can imagine. And imagination, time and again, has proven to be the first step toward discovery. Perhaps the warp drive will never leave the pages of theory. Perhaps it will remain, as it is today, a beautiful idea, elegant, daring, and forever just beyond reach. But even so, it has already done something remarkable. It has united the worlds of science and imagination, drawing together the rigor of physics and the wonder of exploration. It challenges us to think bigger, to ask deeper questions, and to recognize that progress in science often comes not from what we know, but from what we cannot yet explain. In that sense, the warp drive is not a failure of science fiction. It is science fiction at its best, a thought experiment so bold that it forces reality to respond. It keeps scientists honest, dreamers inspired, and humanity pointed toward the stars. Every time we confront an idea that seems impossible, we refine our understanding of the possible. And even if the warp drive never materializes, the pursuit of it will continue to shape the journey of discovery, guiding us, slowly but surely, toward a fuller understanding of the universe and our place within it. Because ultimately, the story of the warp drive isn't about escaping the limits of space. It's about exploring the limits of ourselves, our imagination, our intellect, and our willingness to question everything we think we know. The equations may say, "not yet," but the universe has a way of surprising those who keep asking questions. And as long as we keep looking up at the night sky, wondering how to reach those distant stars, the dream of the warp drive, and everything it represents, will never truly die. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.